Welcome to the Torque and Drag module. This training is divided into 3 sub-modules. This is sub-module 1. In this session, we'll introduce the fundamental concepts of torque and drag in drilling operations, setting the foundation for more advanced applications in the following modules. In this first sub-module on torque and drag, our objectives are focused on building a strong conceptual foundation before moving into applied analysis in later sections. By the end of this session, you should be able to clearly define torque and drag in the context of drilling operations and explain their significance in wellbore mechanics. We will explore the basic components that contribute to drag forces and torque losses, including side forces acting on the drill string and their relationship to wellbore geometry. You will learn how tension, weight distribution, and directional drilling parameters influence sidewall contact forces. This understanding is key, as torque and drag can directly impact drilling efficiency, equipment performance, and ultimately the ability to reach planned targets. Another objective of this submodule is to highlight the practical applications of torque and drag analysis in day-to-day drilling operations. While advanced mathematical models will be addressed in later submodules, here we will focus on understanding the physical concepts, how they are represented, and why they are important to the drilling engineer. Ultimately, this session will prepare you with the knowledge needed to recognize where torque and drag issues may arise, setting the stage for deeper analysis in submodules 2 and 3. Torque and drag are fundamental concepts in directional drilling that describe the mechanical forces acting on the drill string as it interacts with the wellbore. Torque is the rotational force required to turn the drill string at the surface. As we rotate the pipe, frictional resistance builds up along the borehole wall, particularly in deviated and horizontal sections. This resistance increases with well length, contact forces, and borehole curvature. Torque must be carefully monitored because excessive torque can lead to stuck pipe, drill string failure, or reduced efficiency at the bit. Drag, on the other hand, is the axial resistance encountered when moving the drill string vertically, either running in hole, RIH, or pulling out of hole, POOH. Drag arises due to sidewall contact forces and cuttings accumulation and is strongly influenced by the well trajectory. Deviated wells experience higher drag because the string is forced against the borehole wall, creating more contact area and friction. In this slide, we focus on the side force component, which is central to understanding torque and drag. The side force arises when the drill string is deflected against the borehole wall due to well trajectory and applied loads. Now let's look at the different components that contribute to side force along the drill string. First, weight. In deviated or horizontal wells, the drill string's own weight pushes it down onto the low side of the hole. This creates normal contact force with the borehole wall, which drives friction. Next is tension. When the string is under axial load, especially in curved sections, part of that load translates into lateral force. So the higher the tension and the sharper the curve, the greater the side force. Stiffness of the drill string and BHA also plays a role. A stiffer string spans the well path differently, reducing continuous contact but increasing concentrated points of force where it bends. Then we have buckling. Once compression sets in below the neutral point, the pipe can buckle. Sinusoidal buckling increases contact moderately, but helical buckling causes high wall contact and major torque and drag. Dynamic vibration adds to this picture. Stick slip, axial bounce, and lateral whirl all generate spikes in side force, which raise friction and mechanical risk. Hydraulics also matter. Poor hole cleaning leaves cuttings beds that lift and wedge the pipe against the wall, increasing drag. Effective fluid properties can reduce side force by keeping the hole clean and providing lift. Finally, key seating. Continuous side force in doglegs can cut grooves in the formation, trapping tool joints and significantly increasing the risk of sticking. Together, these 7 components define how side forces develop, and they're the drivers of torque and drag problems we see in the field. Analyzing torque and drag has a wide range of applications, and this slide outlines the most important ones. First, we use it to define rig equipment requirements. By predicting torque and drag, we can determine whether the rig has sufficient hook load, rotary torque capacity, and top drive performance to safely reach the planned depth. Second, torque and drag models help us determine the drillability of the well. If predicted forces are too high, the design may not be drillable with the available rig and string configuration. Third, it allows us to optimize the trajectory and BHA, drill string, and bit design. By running scenarios, we can minimize friction, reduce side forces, and improve drilling efficiency. Fourth, we can simulate drilling and completion runs, including casing running, to verify that casing can be successfully deployed to bottom. Fifth, torque and drag help us identify problem areas and circumstances for sticking events by highlighting sections with high side forces, tight doglegs, or poor cleaning potential. Sixth, the model supports mud program needs, ensuring the right lubricity, rheology, and hole cleaning capacity. Finally, torque and drag analysis is used to evaluate hole cleaning actions and determine reaming, back reaming, and short trip requirements, providing a predictive tool to avoid problems before they occur. We'll walk through the 4 diagrams in order and read the resultant vectors from the combined effects of weight W and tension T, as well as their implications. Top left, shallow building section. Here, tension is high in the string. In a building curve that high, axial pull resolves toward the high side, so the resultant vector points strongly into the top of the hole. The sideways component is dominated by tension, not weight. Note the high tensile load indicated by the large blue arrows. The high side force into the top of the hole can result in key seating. The rule of thumb is to keep these doglegs low. Top right, shallow dropping section. Again, high tension dominates. However, in a dropping curve, the axial pull resolves toward the low side, causing the resultant to drive the string into the low side, resulting in a large side force. This case is technically very rare, unless the well was drilled with a slant rig, bottom left. Deep building section, deep building. Here, the local tensile load is small. Only a short length of pipe is below the section. Weight dominates, so the string naturally rests on the low side. The resultant vector points mainly down, low side, with a modest lateral from curvature. As the result vector is low, high doglegs can be used without causing significantly high side forces. Bottom right, deep dropping section, same depth logic, but in a dropping curve, the weight of the tensile load above resolves such that the resultant pulls the string off the bottom, lifting it off the low side toward the high side. Net effect, side contact shifts away from pure low side resting. This can be a problem because the string is unsupported and results in high shock and vibration. This is the side force formula for wall force with pipe tension and dogleg severity. We are calculating the side force, which is the force pushing the drill string against the borehole wall. To do this, we multiply together 3 key factors. First, the dogleg severity. This tells us how sharp the wellbore curve is. The sharper the curve, the more force is directed sideways. Second, the length of the pipe section that spans across the dogleg. A longer section increases the overall side load. Third, the pipe tension, the amount of pull or stretch in the drill string. The higher the tension, the more that side load is magnified. We also include the constant pi in the calculation, which comes from the geometry of the curve, and then we divide the whole expression by 18,000. That denominator is simply a scaling factor to keep the result in the right practical units. So overall, sharper bends, longer spans, and higher tension all increase the side force. Finally, it's important to remember that casing wear becomes a real risk when these side forces exceed about 2,000 pounds per 30 feet of pipe, or 1 metric ton per 10 meters. Beyond this level, we also risk key seating depending on the formation. Let's work through this example step by step to see how the sidewall force is calculated using the side force equation. We are asked to calculate the wall force across a 30-foot section of wellbore with a dogleg severity of 5 degrees per 100 feet. The pipe tension is given as 100,000 pounds, Substituting into the formula, side force equals dogleg severity multiplied by pi, multiplied by section length, multiplied by tension, and then divided by 18,000. The result is about 2,618 pounds of side force per 30 feet of pipe. That tells us how much lateral load the casing or formation wall is experiencing over that interval. Now, if we examine the exercise, we want to determine the maximum dogleg we can apply to maintain a side force below 2,000 pounds per joint of drill pipe. We have a kick-off point at 1,500 feet, building up to 30 degrees at 10,000 feet. The drill string tension at that depth is around 180,000 pounds. If the average joint length is 31 feet and we want to keep the side force below 2,000 pounds per joint, we can rearrange the equation to solve for dogleg severity. Doing that, the maximum DLS comes out at 2.05 degrees per 100 feet. This demonstrates how limiting curvature reduces side force, thereby protecting both the casing and hole stability. Here we compare the soft string model and the stiff string model for torque and drag analysis, focusing on how side forces are represented. Let's begin with the soft string model. In this approach, the drill string is assumed to have no stiffness. It is essentially modeled as a flexible cable lying inside the well bore. Because it cannot resist bending, it is assumed to be in continuous contact with the low side of the hole, regardless of borehole curvature. This makes the mathematics relatively simple, and the soft string model has traditionally been used for quick estimates of torque and drag. However, by treating the string as perfectly flexible, it fails to capture the reality of how pipe stiffness affects actual contact points and side forces. Now let's look at the stiff string model. Here the drill string is considered a beam with stiffness, capable of resisting bending. Instead of assuming continuous contact, the model identifies discrete contact points where the pipe actually touches the borehole wall. This makes the stiff string model more realistic, as it accounts for hole size, tool joint clearance, stiffness, and bending mechanics. Due to this, it is the preferred model in modern engineering, offering more accurate predictions of torque, drag, and side forces. The soft string model has several weaknesses. By ignoring stiffness, the soft string model cannot predict buckling onset, which is critical for drilling performance and mechanical integrity. It also tends to underestimate drill string torque, and it does not properly quantify side forces, leading to errors in wear predictions. Furthermore, it cannot monitor the true stress and fatigue state of the drill string. In summary, while the soft string model is simpler, it is often inadequate for high precision analysis. The stiff string model provides the necessary accuracy to ensure safe, efficient drilling operations. The stiff string model is used by SLB because it is more representative. However, some companies still use the soft string model software because it is easier to compute and apply corrections to obtain a realistic answer. Now let's recall how stiffness is defined for the bottom hole assembly, specifically when considering a drill collar as a hollow cylinder. The stiffness coefficient is expressed as E multiplied by I, where E is Young's modulus and I is the moment of inertia. Young's modulus, measured in pounds per square inch, is a material property that defines elasticity, essentially how much a material resists deformation under stress. For steel drill collars, E is constant, meaning that stiffness is primarily governed by geometry. That brings us to the moment of inertia, I, which captures the resistance of the cross-section to bending. This shows that stiffness increases dramatically with a larger outside diameter, while a larger inside diameter reduces stiffness. For drill collars, this is critical. A collar with a greater wall thickness, meaning a large OD relative to ID, will be much stiffer and better able to resist bending, buckling, and deflection in the well bore. This stiffness is essential for maintaining trajectory control, preventing unplanned doglegs, and ensuring efficient weight transfer to the bit. At the onset of buckling, the first order buckling limit is referred to as sinusoidal buckling. The drill string begins to form a sinusoidal or snaky shape on the low side of the well bore. If the compression continues to increase beyond sinusoidal limits, then at a certain point beyond, the force required to initiate sinusoidal buckling. Helical buckling begins, resulting in spiraling of the drill string around the borehole, causing movement, lockup, as described in coiled tubing, drilling with high side forces and infinite contact points with the wellbore. Buckling can be a significant problem in directional motor drilling. It can result in being unable to slide with the motor assembly through a dramatic increase in drag. In addition, the effects of tool joints with slim pipe may have a significantly reduced impact on buckling resistance. Now, let's review the Dawson-Pasley buckling criteria, which defines the critical sinusoidal buckling load, FCR. This is the load at which the drill string will start to buckle sinusoidally inside the wellbore. The formula expresses FCR as twice the square root of the stiffness and loading terms divided by the radial clearance. Breaking it down, E, Young's modulus, represents material stiffness. Since drill pipe and collars are made of steel, E is constant, meaning that geometry and loads drive most of the variation. I, the moment of inertia, reflects the pipe's resistance to bending. A higher OD or thicker wall greatly increases I, raising the buckling resistance. KB, the buoyancy factor, reduces effective weight in fluid. In high-density mud, buoyancy decreases the compressive force acting on the pipe, delaying buckling. W, the unit weight in air, is scaled by buoyancy and inclination. More weight increases compressive force, reducing stability. Sin theta, the sin of the inclination, shows that buckling risk increases with deviation. At higher angles, more of the pipe's weight acts laterally against the borehole wall. Finally, R, the radial clearance between the tool joint and the hole, appears in the denominator. Larger clearance lowers the critical buckling load, making the pipe more prone to sinusoidal buckling. The picture on the left represents the pipe in sinusoidal buckling. As a certain weight is applied, the pipe transitions into helical buckling. Looking at the Dawson-Pasley buckling criteria, which defines when drill pipe begins to buckle inside the wellbore. The formula gives us the critical buckling load, FCR, which is the axial compressive force needed to initiate sinusoidal buckling. At this point, the pipe starts to bow sideways in a wave-like or snake-like pattern. Contact with the borehole wall becomes intermittent, and we observe an increase in drag. However, the drill string can still transfer weight to the bit reasonably well. However, if compression continues to rise, the pipe will not remain sinusoidal. Once the load exceeds approximately twice the critical buckling load, the drill pipe transitions into a helical buckling mode. In this state, the pipe forms a continuous corkscrew shape around the wellbore wall. Unlike sinusoidal buckling, helical buckling causes continuous contact, which dramatically increases torque and drag. It also reduces the efficiency of weight transfer to the bit and accelerates fatigue loading in the drill string. In summary, the Dawson-Pasley criteria enable us to calculate the point at which sinusoidal buckling begins. If compressive forces then climb to about double that value, the pipe moves into helical buckling, which is far more damaging to drilling performance and drill string integrity. In this submodule, we have focused on understanding how side forces, stiffness, and buckling behavior affect drill string mechanics. We began by calculating sidewall forces by combining pipe tension, section length, and curvature. This allowed us to quantify the lateral loading acting on the borehole wall. We then worked through an example showing how to calculate side force for a given section and how limiting dogleg severity reduces the risk of excessive contact loads. Next, we compared soft string and stiff string models. The soft string model treats the drill string as a flexible cable, continuously in contact with the low side of the hole, but it underestimates torque, cannot capture buckling, and ignores mechanical integrity. The stiff string model, by contrast, incorporates bending stiffness and discrete contact points, making it the preferred approach for torque and drag analysis. We then examined stiffness in drill collars, defining it as Young's modulus multiplied by the moment of inertia, and demonstrated how the outside diameter has the strongest influence on bending resistance. Finally, we reviewed the Dawson-Pasley buckling criteria, which predict the onset of sinusoidal buckling and the transition into helical buckling at higher compressive loads. Together, these concepts provide a framework for anticipating and controlling drill string mechanical behavior in deviated wells. In the next submodule, we will look to explain and define friction factors and understand the causes of torque and drag. This concludes submodule 1 of 3 for torque and drag. Please progress to the quiz. Thank you.